So up next, and the last part of Unit 4, we have El Hospital rule, right? I don't know how to say it. To this day, I don't know how to say it. I've heard it called El Hop, and I've heard it called Hospital rule. I call it Hospital rule because you cannot be bothered to remember this. As long as you remember what it is, and what it does, and what it's for, that's all you need. You don't got to know French. So basically, this is for when you're trying to find the limit of something, and you end up with 0 over 0. If, for example, you're trying to find the limit when x is approaching -6 of this equation right here, x squared plus 5x minus 6 over x plus 6. If you plug it in, you're going to get 36 minus 30 minus 6, which is 0, over -6 plus 6, which is also 0, right? So you can't plug it in here. You get 0 over 0. It doesn't work. If you were to factor it, you would get x minus 6 and x plus 1. And nothing here would cancel the x plus 6, so you can't do that either. So the hospital rule is what you do to solve this. The hospital rule just states that if you derive the top and you derive the bottom, you just get your answer. Like, I don't know why, it's like magic. If we apply this rule, the El Hop rule, to this, and we derive the top, we get 2x plus 5 over 1, and then we can just plug in our limit when x approaches -6, and we'll get -12 plus 5, and we'll end up with -7. This is just our answer. So the El Hop rule makes limits very easy, very simple. You don't have to factor anymore. You don't have to, and you can solve limits that you previously couldn't solve if you factored them. But you just derive the top and you derive the bottom. You don't have to do no quotient rule. You don't have to do nothing hard. You just derive the top and you derive the bottom and you plug in your limit. Okay, so I have 2 more examples up right now. Go ahead, pause it, try it yourself. All right, let's go. So if we plug 2 into this, we can just look at the bottom here. We'll end up with 4 plus 2 minus 6. This ends up as 0. And we can't really factor the top. We can factor x out of the top and make it x squared minus 7x plus 10. And then we can factor out a -2 and a -5. But any -2, -5 don't cancel this. So there's no point in factoring it. So we apply the El Hop rule. So let's derive the top. We'll get 3x squared minus 14x plus 10. And then you derive the bottom, 2x plus 1. We plug in our limit when x is approaching 2. 3x squared is the same as 3 times 4 minus 14 times 2, which is 28, plus 10 over 4 plus 1, which is 5. If we simplify this, we'll end up with -6 over 5. And that's our answer for the first one. So our limit when x is approaching 2 of this function here is -6 over 5 by the El Hop rule. So the second one on the right here is a little bit harder. Obviously we plug in 0, we'll get 0 plus 0 minus 0 over 0 times this 1, which is 0, so end up with 0 over 0. So when you derive this, if deriving the top isn't that hard, it's chain rule, so you get 2 cosine 2z plus 14z minus 2 over, and if we simplify the bottom out here, we could derive it from here and use product rule. I think it's easier to multiply out this z plus 1 squared first and then do it. So if we have z plus 1 times z plus 1, we get z squared plus 2z plus 1. And then we multiply all of this by the z squared up here, and we get z to the 4th plus 2z to the 3rd plus z squared. So now that we have the bottom part simplified, we have to derive this. So we get 4z to the 3rd plus 6z squared plus 2z. And if you look and we plug the limit of 0 into this, it's still not going to work because this denominator here is just going to equal 0 because we have 0 plus 0 plus 0, right? What do we do when we have a limit that we can't solve? We just do El Hop again. So we derive the top. It's chain rule. So you'll end up with -4 sine 2z, because they're the cosine negative sign, plus 14 over 12z squared plus 12z plus 2. And now if we plug our limit when z is approaching 0 back in, sine of 0 is 0, 14 you keep, this is 0, this is 0, so you end up with 14 over 2, or 7. So if you have El Hop and you're using it and you end up with another function that you can't do, another limit that you can't find, you just do El Hop again, and you can do it again, 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 as many times as you need to get to a point where you can actually plug your limit in and solve it. So this is it for El Hop, this is it for Unit 4, pretty simple, pretty fast, we moving on.